Hey, let's think about that Musgrave Ritual again from the very beginning of the lesson. In that one, you'll recall that Sherlock Holmes and his friend Dr. Watson had been asked to solve the Musgrave Ritual, which was a series of clues that took them to this final hidden location. And the question was raised then, well, if Sherlock Holmes actually understood vectors, couldn't he have figured out a way to go directly from his defined starting point to the ending point without doing all that pacing of the Musgrave Ritual? So let's go back and look at the steps of the ritual. The first step of the ritual was 8 by 8 to the west, which meant they had to go 64 paces to the west. So as I read through the ritual, I'm going to go ahead and do a drawing over here on the right. I put in that displacement vector representing 64 paces to the west. The next step in the ritual was to go 49 paces to the south. Then they had to go another 36 paces to the west. Then they had to go 25 paces to the south. And you might recall in the video in this one, that was where they had to get in the boat and glide across the moat to the building because their final destination was behind the door in this building. So they broke down the door and they went another 4 paces. And they had this whole discussion of, oh, Holmes, you forgot the and under. And they remembered, oh, the thing must be down in the cellar of this building. So they went down into the cellar and they found what they were looking for. But the question then comes up, if this was the path that they followed, couldn't they have made it shorter and easier? And we can add the vectors and we can see that there actually is an easier way to do this. First, let's take and rearrange 2 of our vectors so that everything is all nice and perpendicular to each other and we don't have that bend in it. Then we can take those 2 vectors on the top, 36 to the west and 64 to the west, add them up and just replace them with a single displacement vector that would be 113 paces long. Do the same thing with the ones to the south. 49 south plus 25 south plus 4 south is the same thing as 78 to the south. So if we get rid of those 3, we could put in a single vector that's 78 to the south. The resultant then would have been the path that Sherlock Holmes and Watson could have walked directly from their starting point to the end. And we'll draw that one in and we'll just label it R for the resultant. But the question still lingers, well, exactly how many paces would they have to walk to get to the place that they're actually trying to get? Well, notice we've got a right triangle drawn here, and one of the most powerful tools that we know of that deals with right triangles is the Pythagorean Theorem, which is a squared plus b squared equals c squared. If we take it and rearrange it to solve it for c, this is expressed as c is equal to the square root of a squared plus b squared. Then we can substitute our data in. 78 paces south will be A, 113 paces west will be B. So when we put those in, the expression now becomes the resultant is equal to the square root of 78 squared plus 113 squared. So if we then square 78 and 113, 78 squared is 6,084, 113 squared is 12,769. So the expression now becomes the resultant is the square root of 6,084 plus 12,769. If we grab our calculator and add those 2 together, we see that the resultant is now the square root of 18,853. And again on our calculator, just hit the square root button and we find that Holmes and Watson really only needed to walk 137 paces. But the question now is, well, exactly what direction should they have walked? Well, we can look at our diagram here and we can see that this angle theta is on the south side of west. That original 113 pace vector was due west, and they've got to be on the south side of it. But how many degrees? Well, when you have a right triangle, remember we also have some trigonometry laws that are very useful. And this vector of 78 paces to the south happens to be directly on the opposite side of theta. The 113 paces is the side of the triangle that's directly adjacent to theta, and the length of the long side that they're trying to find, r, is the hypotenuse. Well, if you want to know that angle, if you know 2 sides of a triangle, of a right triangle, you can use sine, cosine, or tangent to find it. And actually we've got all 3 sides here, but since the ones that we originally paced out or were from the actual data are the 78 and the 113, that means we've got the opposite side and the adjacent side, and the trig law that deals with opposite and adjacent is tangent. So the tangent of that theta is equal to the opposite side divided by the adjacent side. Substituting our values in, that means the tangent of that theta, the tangent of that angle, is equal to 78 divided by 113. And if we put that in the calculator as 78 divided by 113 and then find the inverse tangent of it, that angle is a 34.6 degree angle. So now we've got everything. If Watson and Holmes had gone 137 paces in a direction of 34.6 degrees south of east, they could have gone directly to the end of the Musgrave Ritual.